Hey, welcome to this Lunchbox on format string vulnerabilities. In this Lunchbox, we're going to be taking a look at what format string vulnerabilities are, how to spot them, how to exploit them, and how to make sure they never get into your code. Specifically, we're going to be looking at 7 high-level topics: format string functions, what they are; parameterization and their types. These are things that we pass to format string functions; direct parameter access, which is an interesting way of formatting the type of parameterization that we give to format string functions. We're going to look at what happens when you don't parameterize correctly. We'll take a look at information disclosure from the stack so we can leak sensitive data. We'll take a look at what a write-what-where primitive is and how to utilize it. And then we'll take a look at a common exploitation vector for format string vulnerabilities, which is a got overwrite. Before we begin, we want to go and point you to hack with code or hacking with code on GitHub. The LunchCTF repo that's there has a format string vulns file. In this file, you have a Docker compose file. You basically just run docker compose up, docker compose build, docker compose up, and then you have your entire environment with all the examples that we use in this Lunchbox. All right, so format string functions are probably something that isn't new to you. If it is, in C, there are certain functions that you can call to work with strings. In this particular case, printf is probably the most well-known, followed by some least or ones that aren't particularly known, like vsprintf. In these particular cases, these functions are designed to take some type of argument or a variable and mash that into a single string that can be printed out. We'll take an example and we'll look at an example in just a second. So the parameterization and types, when we're actually building up a format string, we can specify what types or how we want to format the data that we pass into that format string, like that format string function, like printf. So for example, if I wanted to print an age of somebody, that's a decimal, so I can use %d, but an age is never really negative, so I can use %u if I wanted to, or %c to print out a character. One that you might not have heard of is %n. It doesn't actually print anything, however, it tracks how many bytes would have been printed and then writes that number to a specified pointer. This is a little strange, and it's a key to exploiting format string vulnerabilities. So let's take a look at an example. On line 8, we have a main function that will basically just check to see if we have some type of command line parameter that's passed to this. If not, prints out some usage. Then it'll print hey with the first command line argument that we give to it. It'll pass that into hey as a char star called name, and then it'll take whatever I pass into it and say hey %s. So it's going to format it as a string. So in this example down here, I run example 1 with John, and it'll just say hey John. For an example with using the format specifier %d, this is a little different in the sense that we just use %d and pass an age. Down below on line 11, we call a to I to actually transfer the ASCII input to an integer, so that when we pass it through, %d is matching up with the actual type, which is an int of age. So it'll just print out, hey, you're 22 years old, or whatever you enter in. This is a format string and a format string function. Let's take a look at %n. This one is really strange, but essentially what we'll do is we'll run this application. On line 5, it'll say the value of number is %d. It's initialized to 0, so it'll print down below as 0. This is no surprise. But when we run printf, we'll say lunchctf %n, and we'll give it the address of number, that variable on line 4. What it's going to end up doing is counting the number of characters that would have been printed before that specifier. Since lunchctf is 8 characters, it takes 8 and it'll actually write it to the location of number. And then when we write the value of number again on line 7, it'll be 8. This is a really strange thing. I don't know what reason there was for utilizing this, but apparently it was important enough to include in these format strings as a specifier, and again is very key to us exploiting these, as we'll see in the future here. So one of the things that's really important is that in most cases when we do find a format string vulnerability, there's going to be a limited amount of input characters that we can specify, which means that we need to be really creative in the way that we leverage this concept of a write-what where primitive. If I need to write the value of 3000 to a location, well, I need to write 3000 characters and then a %n to do it. If my buffer is only 256 bytes, I can't actually do that. But it turns out through special formatting options, we can actually do that. And specifically format or direct parameter access and the formatting, specifically the width and the flags, allows us to do this as well. So when we think about a format string function, typically we think of something as simple as %s or %d, but there's a lot more that you can actually modify that with. And this is the actual sort of prototype or function of this. We have % all the way on the left and then type all the way on the right. Type would be our s or our d or our n or whatever. But we can also add parameters to it. The parameters would be in the form of a number followed by a $sign. The flags would be typically 0, and a 0 is essentially used for 0 padding up to a certain length when you want to format stuff. With a width, you can say something like, I want this to always be 8 bytes or 8 characters or 16 characters if you're on a 64-bit system. The precision is the maximum number of characters that will be output. So just like width, we'll say always pad things up to this amount of bytes. Precision will say basically don't go over this particular point. And then the length is basically just things that you might be used to in terms of quad word, integers and longs and stuff like that. So let's take a look at how we can use direct parameter access to do something funky. What we're going to do on line 3 is we have a main function that will then initialize 5 integers. They are num1 through num5, and their values are 1 through 5. We're going to print them as we expect using %d. So we'll have 5 %ds in our format string. These 5 %ds are our format specifiers. And the first %d will take num1, the second %d will take num2, and so on. In the case of direct parameter access, we don't have to follow that order. I can say $n, %n $type. In this case, %for $d will say I want the 4th parameter. So it's going to go to num4 and print that. So the order that we're actually going to print these in is the 4th, the 2nd, the 1st, the 5th, and the 3rd. And if we look down at the example output, we see exactly that arrangement of printing. So we're going to take a look at the importance of parameterization. Basically, this is what a format string vulnerability looks like. They're extremely easy to detect and find. Modern compilers will warn you immediately if there's any issue like this. And there are mitigations or exploit mitigations that are now on by default. But this all assumes that you have a modern system and you're running a modern toolchain, which doesn't always happen, especially on embedded devices where things are being printed to log files and such. So this is still very practical, though it is sort of on its way out as we continue to sort of develop good practices in programming and get modern compilers in the loop. So we have this printf hello $ or %s, which is going to just print out our name. This is fine because whatever a user gives will be parameterized to the %s format. On the second line, where we just give name to printf, this is really bad because we're giving the user complete control over what goes in there. In a sense, they can essentially just define their own format specifier, which is not a good thing, and we'll see why. So in this particular example, example 5, we are going to ask a user for a string, and then we're going to say, watch this, print out that string. Now watch this. We'll print out the same exact thing, but this is going to be a vulnerability on line 7 or an issue here. Essentially, we give the user complete control over what's passed into printf, and then the puts on line 8 is just because I'm OCD and want an extra new line after all the stuff gets printed out. So the cursor isn't right next to everything that I print. It's just for pretty printing format purposes. It doesn't need to be there for this. So if we run this with lunchtf, we're going to see watch this lunchtf, now watch this, ... And then we have lunchtf again. There's no surprise here. But let's take a look at this example where instead we provide a format specifier, a string that we would normally see passed as the first parameter to a printf function. In this case, it says watch this, which is parameterized correctly. Now it says watch this again, and we get some weird character. So what are these weird characters? Well, it turns out these weird characters are whatever the heck happened to be on the stack when it said, I need to pop something off of the stack to then provide to my %s. Since nothing was actually provided, since we controlled the format string, it's just going to take whatever happened to be there at the time. In most cases, those are, well, actually in all cases, those are stack variables, and they're local stack variables. And if we pop enough of those, we can bleed down into other stack frames and eventually make our way to really good, juicy information, as we'll see here in a second. So if we continue this process, doing %s, %s, or %x, %s, whatever we want to do, and then eventually we hit a %n, we'll probably get a seg fault. And the reason is what happens is when we give this particular format string, it'll go, okay, I need to fulfill 5 format specifiers. I have 4 %s's and 1 %n. Now what I want to do is pop 4 D words or 4 quad words, whatever, 4 values off of the stack to facilitate the handling of the %s's. At that point, it'll say, okay, here's how much data has actually been printed at that point. And the %n, to fulfill that, it will pop the next value off of the stack and try to write that value to that as a pointer. Chances are that's probably not an actual valid pointer, or it may not be writable if it is a valid pointer, leading to a seg fault. So we can control this in a very specific manner to get code execution, but that seg fault is key as it gives us indication that something is wrong here. So information disclosure is important because we can essentially leak local variables off the stack. Now, the stack essentially is scratch space for how an application is going to work on data. This could include sensitive keys. It could be flags for CTF problems. It could be, passwords that are being compared via strings or some other type of value that gets stuck there. And typically what will happen is that data will be sensitive, but it'll be stuck on the stack and never presented to a user. So it's sort of quote unquote secure. Those things should essentially be scrubbed before they're given up or given back to the system for security reasons. So we sanitize memory. But as we're working on them, those things sort of need to be there. And if there's a format string vulnerability, we might be able to leak that out in certain cases and get some information that's really important. So let's take a look at some leaking local variables. We have an example here. There is a very specific way that I compile this, which is not at all necessary. Essentially, I'm going to compile a 32-bit binary. This could be 64, it doesn't matter. And I'm going to give GCC this flag or switch that's M preferred stack boundary 2. Essentially, what will happen is your compiler is going to give a certain amount of alignment, usually like 4 D words. In this case, we want to modify that, or we want to change what that actually does to make it a little bit more in line of what we think happens on the stack naturally. There's a lot that happens under the hood. So what I'm telling GCC is, hey, I want you to just obey a stack boundary of 2 to the 2. So just don't worry about what you normally do and get a normal stack boundary. So this will just make the variables that we see show up sooner than they normally would if we don't use this. Basically, don't worry about it. You'll see it in action here. So on line 8, we have int secret 1, which is a bunch of 1s, secret 2, which is a bunch of 2s, and secret 3, which is a bunch of 3s. And then at the end, we're going to say if our input buffer equals any of those secret numbers, then we're going to print out, hey, you found a secret, right? So but imagine we were connecting to the service and we didn't actually know what those secret values are. Because of what happens on line 13, that a buffer that's controlled by a user is passed directly to printf, we can start popping values off of the stack and find those secret numbers. An example here on example 6, I print out A, B, C, D, and then dot, and then I give %x's with dots in between. This is just for a pretty formatting, here. So what's going to happen is we'll see the 1111 or all of the ones as our secret 1. We'll see our secret 2, and then we'll see our secret 3, followed by 4443, 42, and 41. That is DCBA. So Little Indian is flipped in terms of, or x86 is flipped to Little Indian. So ABCD actually shows up as DCBA, which is that. And then the following one after this, the 2E7825 is actually our percent modifiers, percent x modifiers. So what we're starting to do is we're starting to leak data off the stack and actually get into our buffer. Now, the way that the compiler has actually sort of arranged all of this is it has your secret 1, 2, 3 followed by the buffer there, which is sort of maybe a little counterintuitive to what we think about it. We might think that the buffer's there, followed by secret 3, followed by secret 2, followed by secret 1. It all has to do with how the compiler is going to lay all this stuff out for us. This is essentially all kind of inner workings of how GCC is going to lay this out. All right, so if we run a different example or the same example, but we use Python to print out whatever the heck the decimal value is of all ones as a D word, it'll print out the 286331153, which is that value in hex, and it'll say, hey, you found a secret, right? So we were successfully able to leak values off of the stack and then utilize those to change the route of control flow. This is something that just kind of illustrates the fact that we can get sensitive data off of the stack if we need to. So how exactly does this happen? Well, so imagine a normal case where I have something like printf %d, 3% d's with hyphens in the middle. I need to facilitate those %d's, and essentially I need to give it like a var1, a var2, or var, whatever up to that point. In x86 on 32-bit land, your calling conventions are going to push everything to the stack. All the stuff still works in 64-bit, but it's just more intuitive to think about it, I think, in 32-bit land, where you don't have to worry about ABIs and what registers are taking values before calling a function. We'll just assume everything's on the stack for this. So what's going to happen is during normal assembly routines, we're going to push all of those values in reverse order onto the stack. So in preparation for this %d hyphen %d hyphen %d, we're going to push all the variables in reverse order. So var_n goes onto the stack, followed by var2, followed by var1, followed by our format specifier, and then we call printf. Once we're inside of printf, printf will see that the very first value is a format specifier, as it always should be, and then it'll look to obey those format specifiers. If there are 3 format specifiers there, it knows that on the stack there must be 3 format specifiers that were provided to it, and it'll use those to facilitate those format specifiers as it should. But if we don't add those format specifiers and we give a user complete control over what goes into user data, essentially we're just pushing the user data pointer onto the stack followed by printf. And when printf goes to facilitate that, it sees, oh, hey, there's 3 format specifiers here in this example, %x, %x, %x. Well, let me go to the stack, and I'm going to pop 3 values off of that to facilitate these 3 format specifiers. But the problem here is that the programmer never set up those 3 specifiers. What's going to be there is data that is just naturally on the stack at that point. We start to modify the stack pointer and popping values off of the stack to print out into these format strings. So when we have control, we can basically set up our format specifier to pop data off of the stack and print it at any way we see fit. So there's this concept, actually what this gives us in a sense with direct parameter access is a primitive called RightWhat where. It means that we have the ability to write what bytes to some address, where address. So it means that I can write a certain number of bytes and actually control their value to a location that I control as well. Now, it doesn't mean complete reign over everything. Sometimes there are restrictions. I may be only able to print to certain address ranges, or I may be able to only get a certain number of writes or size up to this point. And maybe only certain bytes are allowed, perhaps. A good example in these cases are that null bytes are not allowed because they're the C string null terminator. So if it sees a null byte, it's just going to stop and not copy, right? So there are certain restrictions to this, but a RightWhat where primitive is extremely important in this case. So let's take a look at what this looks like by overriding local variables. Now, this is sort of set up for us, and it makes the RightWhat where extremely easy. but hopefully it kind of illustrates the case. So on line 8, we have a declaration of an integer called magic key, and we set it to 0 as its initialization. We then have line 9, which basically just stores a pointer to that. So we go to magic key and get its address and store it in p magic key. We then have a 64-byte stack buffer on line 10, which is initialized to all null bytes. Then we'll actually print out our magic key, get some data from the user and print it. And if the magic key is not 0, we'll win. But how exactly can you change this? Because nothing ever actually changes magic key. Well, we have to actually change it using a format string vulnerability, which is presented on line 13. So in this particular case, we run example 7. It'll tell us and print us out where that magic key is. In this case, it's FFAA 4964. So what we want to do is keep doing %x's or something to print off the values on the stack so we can try to locate that location or that offset on the stack. In this particular case, it's only one D word away. So in order to access or get magic key to the top of the stack, we just need to push that null value off at the very beginning. So those 8 nulls are essentially just 4 bytes, which are zeros. If we pop that off, then we can write something to the actual location of magic key, which is FFAA 4964, and we can do that with %n. So let's take a look at how we do that. In this particular case, we run example 7 again. It'll tell us where magic key is. Notice the location of magic key has changed. That's not surprising. And then what we write in is 4 A's followed by something that will pop a value off of the stack, followed by %n. And in this case, it actually changed the value to 12. Why did it change the value to 12? Well, as we said before, that %n will take the number of bytes that had been printed up to that point after formatting, and then slap it into the location on top of the stack. Since we popped off that 0 with %08x, that null byte is now gone, and at the very top of the stack is a pointer to our magic key. So when we do a %n, it goes, oh, let's see how many bytes we've written so far. There were 4 A's, followed by a minimum 0 padded to 8 characters of the first thing on the stack, which was a null byte. So printed out 8 characters. 8 characters plus 4s are 12. And then from there, it'll say, okay, now I have 12 things that I would have written. Let me go to the next value on the top of the stack, which happens to point to magic key, and I'm going to put the value 12 there. So at this point, it changes the value of a local variable, and we get different control flow here, printing out you win magic key equals 12. Now, this is all great and all, but that requires all very special cases in order to exploit. Well, it turns out that in ELF binaries, there's 2 very interesting ways of linking the actual binary, right? So we have this sort of lazy method and this eager or now method. In the lazy method, imagine we have an application that takes a whole bunch of stuff from the standard library, maybe an encryption library, and all of this stuff. So there's all these different things that should be resolved during runtime. To save us time on startup, what we'll end up doing is basically just saying, hey, listen, I have this global offset table where I know things are going to be located eventually. I have all these functions that I want to use from all these different libraries, but I don't want to waste the time and overhead of going on startup and resolving all of those things, especially when the user may never actually use them, right? So there's specific code paths that we can exercise that we may never exercise half of those things that we import. So why put all of the time and effort into going and resolving all of these locations for imported functions when we can just wait until we use it? And that's what lazy linking is. In a sense, it basically waits until it's about to use it, and then it goes, oh, I need to go resolve this. And then it'll go and resolve it. And then every time it uses it after that, it doesn't have to resolve it again because it's already done it, rather than doing it all up front, which is our eager method or this now method. So the lazy waits for all of these imported calls to be made before resolving it. This can save a lot of time on startup because we may never actually use a lot of those calls, right? So eager will resolve everything on startup. The problem with using lazy, and we think it's actually a really nice optimization, because if you never use any of those things, you shouldn't have to wait or do all those extra cycles in order to start the application up and get it running. With lazy linking, it means that the table that holds all of these offsets or locations to these variables, these these functions that are imported, has to remain writable. Because if it's not writable, then there's no way that we can actually resolve and update the table later on. So this means that when lazy linking is used, we can actually write to this table ourselves if we have a RightWhat where primitive. That table where all of this stuff goes is called the global object table, or global offset table. Actually, that's incorrect. So in a sense, what we'll end up doing is just changing where things should normally go. So if a function wants to call, application wants to call exit, for example, what we can do is, before we call that exit, when we have our format vulnerability or format string vulnerability, we can go to that offset table and we can write a value to it ourselves, so that when it goes to exit, it goes, hey, I already have this, and then it just jumps to us. So using a got overwrite, we can essentially overwrite the pointer of a legitimate function and go to a pointer where we control. A mitigation for this is something called relro, or relocation read-only. It essentially forces eager linking and then marks the global offset table as read-only. So essentially, it does take that performance hit or that impact on startup to go and resolve everything, and then it goes, hey, check this out, modifies the got as read-only, so that way you cannot write to it unless you go through the hassle of marking that area as writable. This is certainly, or at this point now, default in newer versions of GCC. If you step back to a slightly older version of Ubuntu and then just install GCC from app packages, you will get a version of GCC that does not enforce this. So for a very long time, relro was not enforcing or partial, which would allow you to do this no problem. On modern versions of GCC, relro is on by default, so you'd have to specifically turn it off. So what we're going to do is, that's the end of this particular slideshow here. So we can slide over and take a look at what something like this looks like with example 8. Thought it would be easier to actually show in the example rather than having to deal with this in a slide. So if I do this, AAA%N, we get an exception. So let's go ahead and cat out what example 8 actually looks like. So what we have here is all of this stuff. Here's some notes that I've taken on how to actually do all of this stuff. We have the way that all of this is compiled. And essentially what's going to happen is, on the main function, we're going to call this vuln function. Up in vuln, we're going to create a buffer, a stack-based buffer that's 512 bytes. Then we're going to get some input from the user, and we're going to print that out here. Then it's going to say about to call, and then it's going to give you the value of exit, and then it's going to call exit to exit the application. Now up here is where we want to get, which is code execution redirected, you win, and then it calls underscore exit. So exit and underscore exit are actually two different things. Exit will perform some cleanup operations. You can specify certain things to fire at exit, which the normal version of exit will obey. Underscore exit is for exiting child processes. Basically, it's like a oh shit button. It basically says get out now. So without doing any of this and obeying the at exit. So underscore exit is just a I'm out, peace, goodbye. Whereas exit is, hold on, let me do some housekeeping first, and then I'll exit. So what we're going to do is, there are actually going to be two different entries in the global offset table here for exit and underscore exit. We're only going to overwrite the value of exit. What we're going to do is, we're going to overwrite the value of exit to the value of hello. What this means is, inside of here, we're going to call vuln. We're going to set up this buffer. We're going to be asked for something. What we're going to do is give it a payload that will set up a format specifier or format string that will strategically go to the global offset table and overwrite the value there of exit with the value of hello. So that way, when this gets done printing, it'll go to call exit, but exit has not been resolved correctly, or it's been overwritten by us, and then it'll call hello. So how on earth do you orchestrate all of this stuff, and what does all of this stuff down here mean? Well, what we can do is we have objdump, and we have different utilities to find locations of different things inside of executables. So in this particular case, I'll use objdump. I'll use readelf-a. There's a whole suite of tools that allow us to do things like this. So what I'm going to do is just grep for hello. So hello is right here, which is this address. So I know that at all points, hello is going to be at this location on in the binary. So if I go back and cat this example, I already have the value of hello right here listed here. So if I go and do the same thing for exit, we'll see that the location of exit is 0804 A014, which I've put here. So now what we need to do is we need to go and modify exit with the value of this. There's sort of a problem here because we have to do this in a very specific way, and I'll show you why. If I go ahead and print out the value, the decimal value of the location where hello is, it's a very large number. So in order to make all of this stuff happen as a single write, we would have to print this number of characters to the screen before doing this. This is something that would take forever if it's even possible at all. I'm not sure that it actually is. So what we want to do is be a little bit more creative. Using direct parameter access, what we can actually do is write the location of exit or overwrite it 1 byte at a time with the different values that we need to make this exploit extremely fast, right? So the way that we're going to do that is I'm going to say, all right, the hello byte is, the first one is 8, which comes from here. The second one is 4, which comes from here. The third one is 84, which comes from here. And then the fourth one is C4, which comes from here. And I have their decimal values here. What we're going to do is, since we're going to put, we have to put the location where we want to write that. So this value right here is the little endian value of this guy. So 0804 A014. And then I'm going to move over 1 byte to 15, move over 1 byte to 16, then move over 1 byte to 17. And those are going to be the values that we're going to put a %n on, right? So I'll put all of those in there, and then I'll put all these %n's. So when it gets to a location, it's going to go to %n with a direct parameter access to this location, and then write a value there. And then it'll go to %n with direct parameter access to this location, and then write a byte there. And it'll keep doing that over and over and over again, or actually 4 times, until it finally writes all 4 bytes at the location of exit in the GOT. All right. So the way that we do this is we already have the 2 offsets and locations in our binary where this stuff occurs. I have to account for the fact that we're writing 4 4-byte values before I have my format specifiers, which is all of this guy, right? So this is where the 4 plus 4 plus 4 comes from. Now I need a C4 byte, and I need a C4 byte because I want to overwrite what the 14 that should be there. And by there, I mean at this location with the C4. Well, C4 in decimal is 196. So if we try to solve for X here, basically just 196 minus 16 is going to be 180. So if I write 180 bytes before I get to this location, it'll say I've already written this for, this for, this for, and this for, and then another 180, which will give us 196. And then when I specify I want to write 1 byte, the %1, $180 is 180 bytes to an offset of 7. So it's going to pop, or it's going to look past a certain number of values on the stack and go directly to the 7th one, which is where this guy lies. And then it's going to write that byte or that value, which is going to end up being C4 to that location. It's kind of crazy how this all ends up working. So then the next one, we want to write an 84. And 84 is 132, but 132 is less than 180. We've already written a bunch up to this point, right? So we've already written 196 bytes, but now we need to write an 84, which is 132 bytes. So how do we avoid this? Well, since we're only writing one byte at a time, we can actually overflow or just go way past that. So we say, all right, what we're going to do is we're going to write 388, which is not 84, it's 184, but it'll only write the low byte. So it doesn't matter what the heck this is, or this is, or this is. It just matters what that low byte is, because that's the only thing that's actually that we're going to be writing, which is this %1 here. So in that sense, we can basically just make this a larger value so that it increases to the next point that'll give us a hex value that matches the byte that we want to write. And then we continue this process all the way down until we have something sort of filled out here for us to do. So how do we know that this is at 7 and this is at 8 and this is at 9 and so on and so forth? Well, one of the ways that we can do that is by testing where our input is. So if I run this example, which I believe was example 8, I'm going to do 4 A's, which is going to kind of set me up. It's going to put a value on the stack, which will normally sort of take a placeholder of this value. And then I'm going to give it %08x because I want to format this a little bit nicer for us to see. And then I'm going to go ahead and add quite a few of these. All right, so we've added 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're going to look 10 places down the stack. Now, this is something that I wrote. That's a static constant value. And then this %x right here corresponds to the top value on the stack. That's at offset 1. This is at offset 2, offset 3, 4, 5, 6. And then finally, I hit my %A or my A's at offset 7. So what I'm going to be doing here is looking to say, all right, for direct parameter access, I want you to write 1 byte, but use the formatting. I want you to pad the amount of bytes that we've written so far up to 180 maximum or minimum. And then I want you to jump to the 7th location on the stack, which again, down here, 1, 2, 3, 4, 5, 6, and 7. And then I want you to write the value that we've written up to that point to there. So basically, if I did this as my input, it's going to crash because it's going to try to write 180 to 41, 41, 41, 41, which is no bueno. So what we need to do is actually replace that with a location that we control. And the location that we control here is the first byte and exit. And then we shift over to the second byte and exit, the third byte and exit, the fourth byte and exit, and then we write these all the way up. So if I take this example here and I end up writing it, what this is going to end up doing is just printing out using Python to print these non-printable characters and then echo it out into example. And what happens is we end up printing this really long kind of gargantuan thing here. And then it says, I'm about to call this exit function. And then it says code execution redirected. You win, which if we remember from example 8 and the source code here was what hello does. So effectively, we were able to overwrite the location of exit in the GOT to redirect execution to hello, which printed out what we wanted to. In this sense, we can also actually set up our stack with a value of like bin sh and then call system. Because libc imports by default on these things, we can actually just use system even when system may not actually be called in specific cases. So let me load up GDB, for example, 8. I'll set a breakpoint on main. We'll run to that location, and I'll do p for print, and then hello. So hello is at this location. If I do the same thing for exit, that'll tell me that exit is this location. That is the resolved location of where exit actually exists. And I can do the same thing for system, even though system is not actually used. So again, this doesn't match the value of what we saw because the value that we're using is the location in the GOT. This is after it's actually already been resolved for us. So this is how GOT overwrites work, and this is how format string vulnerabilities can be exploited. If you want to try it yourself, head on over to the GitHub page, clone that repo, run everything through Docker, and you can explore at your leisure. Thanks. I hope you learned something new.